Welcome to CS571. So in today's lecture, we're gonna talk about two things. So first of all, we're gonna finish the last topic, which is memory management, specifically page replacement policies. And then the second half of today's lecture, we're gonna move to a brand new topic, which is also the final topic of this semester, which is IOs and storage. Okay, so specifically in this video, we're going to first talk about the very first two fundamental page replacement policies, namely first in, first out FIFO and the random policies. So the very first question to ask about and also to answer throughout the first several videos of today's lecture is to basically ask what data to evict out and what data to keep within the limited memory capacity. Okay. So this has something to do with what is called page replacement mechanism. So specifically in this slide, we're talking about mechanisms. Okay. If you take a look at the very first bullet, it talks about page replacement completes the separation between the logical or virtual memory and the physical memory. So how to understand this? Well, you could, as we've already learned from the previous lectures, a logical memory is some virtual concept. It doesn't physically exist. It doesn't physically exist in the form of let's say a hardware or something. It's just a virtual concept, which is nothing but a few register values, a few pointers, a few bookkeeping metadata information that is maintained as part of the context information for a particular process from the underlying operating system perspective, right? So the logical memory typically has a larger capacity, even though it's virtual capacity, which is bigger than that of the physical memory. So with that, we could say a logical memory kind of consists of the physical memory part together with an extension to the physical memory. And this particular extension is what? Is like we've already discussed in our previous lecture. It's some, it takes use of a part of the external storage space, for example, hard disk drive, as something called the swapping space, right? Swapping partition. It uses a swapping partition effectively as an extension to the physical memory. So these two parts, it construct what is called logical memory. So if I draw it, let's say this is the virtual memory, right? This is a virtual memory. And the virtual memory, it has a larger capacity than the physical memory. And this part gets effectively mapped to essentially physical memory. And the rest of the part mapped to, let's say, a hard disk drive. And this is a swap. Okay. And this whole thing is a logical memory. As you can see, it uses the page replacement policy or page replacement components to kind of, complete the separation between the logical memory, to kind of, make the capacity of the virtual memory larger than that of the physical memory. Okay. And of course, if you want to use an extremely slow, persistent short medium as an extension to the physical memory, of course, it would have impact on the workload or application's performance, right? So let's say if you have already reached the maximum capacity of the physical memory, then you have to make the decision with regards to which exact page you want to evict out from the main memory, right? So if you take a look at this bullet, if there are no free memory, basically it would incur exactly 2 page transfers at this page fault. And this particular event is called page fault, like something we've already discussed in the previous lecture. So why there are 2 page transfers? Well, the very first page transfer is because you want to first evict something out from the memory to the disk. And this is the first page transfer. And then the second page transfer is you want to bring something in. You want to bring in the data of request, the data of interest. So this is a second page transfer. Okay, so this is for the most typical scenario. But we could always do optimization to further optimize performance and further reduce this page transfer or I/O overhead. So the optimization is called the modified bit or the dirty bit, right? So how it works is we embed this modified bit as part of the metadata within its page table, which is the indexing data structure that is used to provide the page address translation from the virtual address to the physical address, right? So assuming all the data are initially brought in from the external storage into the memory. So if the data residing within memory has not been modified by the application or by the program, we don't change the operating system doesn't change the dirty bit. So the dirty bit remains 0. But what if the operating system, what if the application or program explicitly modify the data within a particular physical memory frame? Then the operating system would flip this dirty bit or modified bit from 0 to 1, indicating the data has already been updated, or the data has already been dirty. So this way, if unfortunately this dirty page is picked by operating system as a page replacement target or page replacement victim to evict out, then you have to faithfully write the data out to the disk, right? Because you want to keep the data consistency. You don't want to lose this state that you have just updated by your program, by the application, right? This is on if the data has already been modified. But on the other hand, if the data hasn't been updated, meaning the dirty bit is 0. So even though if the page has been picked by the operating system as a victim to be evicted out, so the optimization works in a way that you don't have to write the data out, because the state is already consistent and there's not any update made to this particular page. So this way, you basically save 1 extra page transfer. Basically, you save 1 disk I/O. So this is how exactly this optimization works, right? So this slide, it basically talks about the policy part. So like the previous one, we've talked about mechanism, the saying, the facilities. And this page talks about the policy, the thinking part. Okay, if we wanna formalize the page replacement problem, so we basically formalize it as some sort of cache management problem, in a way that the physical memory can be treated as some faster in-memory cache for this whole virtual memory systems. And recall that the virtual memory consists of 2 parts. The first part is the faster cache part. And the second part is a relatively slower backing store, persistent storage, for example, hard disk drive or flash SSDs and whatever, okay? And the ultimate objective of page replacement policies is basically to improve performance and reduce overhead, reduce cost. Improve performance, improve efficiency, and reduce the runtime cost as much as possible, okay? And so the performance and efficiency metric, the higher the better, whereas the cost metric, the lower the better, okay? So some common goal whenever we're talking about page replacement policy or caching policies is to, minimize the cache miss rate, or maximize the cache hit rate, right? So how to understand this is to that it tries to minimize the total number of times that the operating system has to read a page out from disk, basically to minimize the total number of IOs hitting on disk, right? So this is the ultimate goal of a page replacement policy. So how to basically model the performance is by using this metric, which is called AMAT, or average memory access time, or you could also call it effective memory access time, okay? So how to calculate this is by referring to this equation. So this equation has two parts, two factors. The left factor is the what if there's a hit, and the second factor is what if there's a miss, right? If you take a look at TM, so basically TM is the cost of accessing the faster piece, the faster part, which is the memory part, and TD is the cost or the latency of accessing the slower part, accessing basically external secondary persistent storage, in our case hard disk drive, okay? And there are also possibilities or chances of there's a hit or chances of there's a miss, right? So P hit is the probability of finding the data or locating the data within the faster memory cache. So this is in correspondence with a cache hit. So P miss is otherwise the probability or the chances of not being able to find the interested data within the memory cache. So in other words, there is a memory cache miss. So it's also called miss rate, okay? So in next slide, let's take a look at one example. So in this example, assuming the cost of getting a memory access, TM, is 100 nanoseconds, okay? 100 ns. Whereas TD, the latency of getting access to something stored on disk is 10 milliseconds or 10 ms. So these two performance metrics, these two different performance metrics, they are dramatically different, like many orders of magnitudes different, okay? And the second factor, the second part that you need to take into account is the probability, the miss rate or the hit rate. So if you know the hit rate, and by default you know the miss rate, because the miss rate is just 1 minus hit rate. So in this case, hit rate or the probability of getting something in the cache is 90% or 0.9, right? So correspondingly, the miss rate is 1 minus 0.9 gives you 0.1 or 10%. Okay? So how to calculate this model, AMAT, effective average memory access time, is by just applying the equation that we've discussed in the previous slides, okay? So the hit rate times the cost to get access within the memory plus the miss rate times the cost of getting access to the hard disk drive, So the first part gives you effectively 90 nanosecond, and the second part gives you 1 millisecond. As you can see, obviously, the second factor is a dominating factor. Because it is just too much larger compared to the very first factor. As a result, the final result is almost like the second factor, the dominating factor. This is just because the disk is just too slow, right? So this is under the condition where the H ratio is 90%. But what if we do some optimization to effectively bring up the hit ratio from 90% to say 99.9%, which is almost 100%, okay? So the results dramatically change from what we've previously seen, which is 1 milliseconds to 10 microsecond, right? So this unit is microsecond. So this 10 microsecond compared to 1 millisecond, there is a 100 times performance improvement, or the latency drop down, right? So roughly it leads to a 100 times performance improvement, as you can see. If you could somehow effectively improve the cache hit ratio or reduce the cache miss ratio by just a little bit, let's say 5% or 10%, the ultimate result is, the ultimate effect is huge. It could effectively lead to 10 times or even 100 times or even thousands of times of performance improvement. And the root reason of this is because of this significant performance gap between the faster storage medium, which is memory, and the slower storage medium, which is hard disk drive. Okay, so let's next take a look at our very first basic cache replacement policy, FIFO. So FIFO is one of the simplest fundamental page replacement policies. Its idea is really straightforward. You just evict the items strictly based on the order they were inserted into the cache. Okay, so how to implement that is you can just use a FIFO queue, right? So this queue just holds the identifiers for all the pages within the memory. So this queue is kind of like a page table, which is an indexing data structure, which is basically sorted. And whenever you want to make eviction decision, just refer to this queue and just evict the top of the queue or the head of the queue, which tends to be, you know, the oldest data that you have inserted into the cache. Okay, the head of the queue. So this is how it works. So in this slide, we're going to use a really simple toil-like example, which is shown in this second bullet as an example to walk through how exactly FIFO page replacement policy works. Okay, so the example workload is like, it's just a string of integers, right? So where each integer is corresponding with a logical address access, a memory access to some logical address within the virtual memory. Okay, so here assuming everything is about logical or virtual address, okay? Starting with 0, moving on to the next one, 1, 2, 0, 1, 3, 0, 3, 1, 2, 1, something like that, and dot, 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 okay? So, at the bottom half of the slide, we're looking at a cache access table, which is used to track the cache behavior. So it has multiple columns. The leftmost column is essentially the example workload, okay, the access. And we have the second column. It indicates whether this access is a cache hit or a miss, right? And the third column, it keeps track of the eviction activities, eviction operations. Whenever the cache is full, you have to pick a victim and evict it out to make room for accommodating new requests, right? And we have the fourth, the rightmost column is the resulting cache state, which is one of the most important contexts that we are interested in looking at. And here, the assumption is the cache size is 3, which is relatively small, which is, kind of, large enough considering this example workload. Okay, so let's first take a look at the very first few workload memory accesses. So the first three, 0, 1, 2. Okay, assuming the cache starts off with an empty state. So that means the very first few cache memory accesses, they are always cache misses. Why? This is because the cache starts off with empty state. These are also called compulsory misses. So how to understand this is you can understand in a way that these few memory accesses are some, some performance costs that you always have to pay because the memory is essentially starting off with an empty state. Everything is initially stored in disk. Okay, if you take a look at the resulting cache state, we recall that this is FIFO, so we need to maintain a FIFO queue, first in, first out. And the leftmost part is the head of the queue, which points to the very first, the oldest item inserted into the cache. In this case, is 0. Okay, so this is the first in part, the first in direction. And the next axis is 0, sorry. So obviously there would be a cache hit for 0 because 0 is the very first item that has been inserted. Okay, and the next axis, which is 1. And since 1 is over here, so there would be another cache hit, right? And next, we take a look at 3. So just examine the context, the state of the cache. The 0, 1, 2, there's no 3, so that means the cache has to make eviction decision to first evict out something, make new room, so that it can accommodate this new access, which is 3. Okay, in this case, because we're talking about FIFO, you need to just evict the oldest, which is 0. So in this case, there is a miss, and just evict out the oldest, the first in, which is 0, and push in something new, which turns out to be 3 at the tail of the cache, at the tail of the queue. Okay, and right now the new head is what? The new head is the oldest item among all that are currently residing within the cache. Okay, so you just apply the same policy, the same rule back and forth. So that is the final result, where we end up having a total number of 4 evictions or 4 misses, not counting the very first 3 compulsory misses. It still incurred 4 actual cache misses. Okay, so this is the result of a FIFO policy. So FIFO policy as one of the simplest cache replacement policies, it has some fundamental issue. And the very first issue is the oldest page, it sometimes may contain heavily used data, or the oldest page might not necessarily be the most useless data, right? So that implies that sometimes we need to bring back that particular oldest page in the near future, because in the near future it is reused. It will be reused in the near future. Okay. So if you take a look at, with that, keep that in mind. If you take a look at this example, these 2 examples. So here we're looking at a different example workload. Okay, this workload has some tricky pattern, but so these the memory accesses, they are sort of following some sequential pattern, right? And again, we apply FIFO policy. And the bottom half of the slide, it shows two tables. The left table, it shows the cache simulation under a cache capacity of 3. And the right table shows the simulation result under a cache capacity of 4, right? So I'm not going to walk you through the exactly each and every like detailed step of how FIFO works because it's straightforward, it's naive, right? So let's directly jump to the result. So this is the result from the left table with a cache size of 3. So keep in mind that we end up having a total number of 3 hits, right? So the hits is over here. So if you take a look at the second column, for yes, it means a hit. Then if you take a look at the right table, even though we have a relatively larger cache size, which has exactly 4 slots compared to 3 slots on the left-hand side, we unfortunately end up with less performance. Why? Because if you take a look at this, second column of the table, we just end up with a total number of 2 cache hits, right? And this is given under exactly the same workload. So the interesting observation of these experiments, the simulation results, is that even though you're given a larger cache size under FIFO policy, sometimes you end up with worse performance, right? So this is something interesting to learn. This scenario is also called Belady's anomaly. And remember the noun here, Belady. So Belady was an IBM researcher, and he has contributed a lot to page replacement and memory cache management research. And in the next couple of videos, we'll be talking more about Belady's offline algorithm, okay? But here, a Belady's anomaly is a term that is used to describe what we have seen in the previous slide. Where essentially, the program runs potentially slower with even more memory. So this is something called Belady's anomaly, right? So in that previous examples, with a cache size of 3, where the cache is able to cache 3 physical frames, it results in 9 page faults or 9 cache misses. Whereas you have a relatively larger cache size where you could hold like 1 more physical frame by holding a total of 4 physical frames. You end up with even lower performance where you have 10 page faults, okay? And so the root reason of Belady's anomaly is because of these 2 different factors. One is you have to, the workload is tricky. The workload is something like the above. It exhibits some sort of, sequential pattern, like looping back 1, 2, 3, 4, and eventually it loops back to 1, and then followed by another, sequential access, sequential scan. And another factor is the total working set size of this workload should be, slightly bigger than the cache capacity. In this example, the cache size is 4, right? But the working set size of this workload. So first of all, what is the definition of the working set size? So working set size is a total number of unique items that you've observed within a limited time window of a particular workload. In this case, if we count this as a time window, the size of working set size is 5, right? Because it covers a total number of 5 unique items. 1, 2, 3, 4, 5. And those repetitive accesses to some existing item, for example, repetitive access to 1, you just count 1 exactly once without duplicating the accesses. Okay, so this is working set size. So the working set size is 5, which is slightly larger than the capacity of the cache, which, has a large chance to lead to this scenario, which is called Belady's anomaly. And this is something interesting to, always learn about. Okay, so next, let's move on to the second basic cache replacement policy, which is called random. Idea is, again, really straightforward. You just pick a random page. You just run this pseudo-random number generator and pick whatever page that is returned by the random number generator and replace it. Okay. It's also also simple to implement, just like FIFO-Q. And there's no intelligence at all of trying to preserving, locality usefulness or, some metric. There's no intelligence at all. Okay, so let's again take a look at this old simple toy-like example. So over here, it shows the same cache trace, cache simulation table, okay, but under a different policy, which is random policy. The first 3 are compulsory misses, which is fine. And then there are 2 hits because 0, 1, they have already cached within the cached within the memory. And a 3, there would be a miss. Right over here, you just end up picking 0 as a victim, and this is completely random, right? Random. And then there's another miss, 0. It tends to be something that you've just evicted out, right? Then you evict it out again. And then you try to bring it in and evict out 1, which is another random decision-making process. And over here, there's a third non-compulsory miss. Okay, over here you just make another random decision, which turns out to be physical freak number 3. Okay, so this is how random policy works, which is really simple. Okay, and in this slide, it tried to quantify the performance of a typical random policy implementation. And the takeaway upfront is the performance completely depends on how lucky you are, right? Okay, if you're using random, then luck is your friend. And also, of course, the workload. If you happen to have a workload that just fits in this random policy, well, it tends to get, some better performance. If you take a look at this plot showing this slide, it has 2 dimensions. The x dimension is total number of hits, right? But this is essentially a histogram. And the y dimension is the frequency. So the frequency as a function of this number of hits shown on the x dimension, okay? So as you can see, so this is some random performance over 10,000 trials, over 10,000 times of runs of the same random policy. As you can see, towards the right-hand side, you tend to have better performance. And over here, 7 is the best. Towards the left end, this is the worst performance that you can have. A 0 cache hit, or all memory accesses, there are cache misses. And this is something impossible to achieve. And over here, as you can see, so the total number of 6 tends to be the optimal. And as you can see, like more than 40 times out of this 10,000, more than 40% out of this 10,000 trials. the performance is approaching optimal. And but on the other end of the spectrum, we have extremely bad performance. Okay, so a cache hit of 2 or 3. It means sometimes a random policy use leads to extremely bad performance, and this is completely depending on like possibility or how lucky you are. Okay.